Okay, so now there's a question here. We would like, based on this data here, we would like to determine the processing time at two different processing temperature. One is 121 degrees Celsius, that's the usual steam temperature, and let's say that the machine was not working properly and the temperature dropped to 97 degrees Celsius. So we would like to adjust our cooking time because everything is ready. We've loaded our food into the retort, ready to go. Let's just adjust our cooking time to achieve the same safety level. And so what is 5 cook time? 5 cook time. 5 cook time is cooking the food for 5D. So 5D, that would let us think about, perhaps now we need to determine what is the D value at 121 degrees Celsius and also the D value at 97 degrees Celsius. And we have this. We have the experimental data from at 90 degrees Celsius, 95, 100, and 105. We have done a triplicate. We've got D value at 90, 95. We can sort of guess that 97, the number is somewhere in the middle, in between. 121, we will need to do some extrapolation based on the data curve. So to make this a little easier, I've already plotted part of the Z value curve, thermal depth curve, but what is here? What should I put in here? Again, remember this is a logarithmic scale. Every major scales from here to here will increase by a factor of 10. And I've done some data, I've plotted some data here just to make it slightly easier, but I don't want to make it easier. Let me just erase this here now. Okay, so let's look at how should we set the scales here. Our largest number here is close to 1,000, okay, and our smallest number here hover around 1, okay. So maybe we should set this here as 1, okay, and then each scales going up is 1.1 here, 1.2 here, 1.3, 4, 5, 6, 7, 8, 9, 10. So up to here now, this is 10. So let me just put a small mark here. This means 1.1. Likewise, from 10, we have 20, 30, 40, 50, 100. 100, 200, 3, 4, 5, 6, 7, 8, 9, 10, 1,000. So on this particular graph, we only really need to reach from the range of here from approximately 1 to 1,000. That's where our data point will be. And if we set our data graph this way, we will have sufficient space to do construct our curve. Just a quick result. Now let's do 850, 910, and 930 here. So again, this is 200, 300, 400, 5, 6, 7, 8, 7, 8, 9. 900 is around here. The graph, I have to say, the data points are very close together. Very good lab scales has been done. So it's not going to be exact. This is a rough idea to show you how to construct the graph. So just try your best to get 850, 910, and 930. So you have 3 data points somewhere that is not very accurate on the screen. 95 degrees Celsius. So this is an experiment done over a range of temperature. So 95 degrees Celsius, we will have 105. 105, a little bit above 100. 92. Oh, 92 would be a little bit below. Oh, I am a little too ambitious there. So here. Okay, roughly, it's not very accurate. So remember, this is just 105, and here is 200. So the level of accuracy here is not there on this graph with my thick pen here. And then again, I will do 7.6, 9.3, 9.8, 1.25, 0.83, and 0.78. well, on the midterm and as on your homework, you will try to draw a best fit curve here. A best fit curve will be something that hopefully that will go between the range of your data here, between, if your straight line should go through this, with trying to fit them through most data point. There will be outlier in our experiment. There will be sometimes it's not unusual that we will have one that is quite far out of your data set. But again, we will try to draw something that is going through our data set. I don't have a ruler here. Use your ruler at home or use your Excel. That will be the most accurate, and try to draw your best fit line. Let me do my best here. So Judy is just trying to draw the best. Oh, this is not even straight, but you get the idea. It should be a straight line. It's going to be a linear curve, and by looking at the linear curve, we will help us to get the Z value. We can do it by calculation, and your Z is going to be, that we have to look for a slope first. The slope is going to be here, so equals to. So a slope, like any mathematical experiment, rise over 1. So what we can do is take data points here and here. So it's the log number of the number of survivors. So this is number, no, this is D value here, D. Okay, so we will take the log D. Let me find a better pen. Let me see if orange would do better here. Just because, oh, orange would do a lot better. So log D2 minus log D1 over T2 minus temperature 2 minus temperature 1. So again, this is data point 2, this is data point 1. You can just pick any one, look for the X and Y axis, then you can look for M. And Z is going to be negative 1 over M. Okay, we can, with the data graph here, we can also look for our Z value visually. A Z is a reduction of the D. A Z is a reduction of D over a log cycle. So we can pick a number here from 100, whoopsie, from 100 here, and then we can pick a number from 10, okay, I'm trying to make a straight line here, okay. Okay, so the temperature difference that will allow us to have a 1 log reduction of the thermal death time. So the temperature difference here is from here to here, and that's our Z. Okay. So by either visually inspecting the graph or by using a set of calculation, we can find the Z value. And now, so this is Z. Okay, now what do we do? Now that we know Z, then we can calculate the D value for at 121 degrees Celsius. And the equation that we are going to use, so what is D at 121? It equals to, again, pick a point. Since we've already done the line at 100 already, so we can pick a point at 100. So we find out what is the D value at 100. Okay, and then we will do 100. Oh, this is an exponent. 100 minus 121 over Z. Then we can find the D value of 121. After that, then as I simply, because we want to achieve a 5 Cope cycle, so it will be 5, it will be this number, D value at 121 times 5. That would be the time it takes to process the food at 121. That's our ideal temperature. As you can imagine, it's going to be a very small number. because at 100 degrees Celsius, it takes about 10 minutes, 105 is 1 minute. We can imagine, trying to imagine that at 110 is going to be 0.1 minute. 115 will be 0.01. Very unwanting of space. And then 120 will be 0.001. So we are talking about less than a second time. We need a matter of seconds to process our food. Even if we times it by 5, it's a matter of a few seconds. But if now that our machine is broken, we have to process our food at 97 degrees Celsius, we can do the same. We can use the same calculation here to get the at 97. We can use the same baseline here at D100 as the same equation. But because we have the graph here, we can simply take advantage of the graph and take advantage of the fact that we can do visual inspection. So we can just look for 97 degrees Celsius here. And so this is 97. Sorry, again, it's hard to get the very precise drawing on this graph. So we will go at 97, go up here, where the linear curve, the supposedly very linear and strict curve is, and then we can determine the D value by visually inspecting the graph, 97 degrees Celsius up here, and trying to find the D. So again, this is 10, this is 20. So it looks like it's fall quite nicely right on top of 30 here. So 30 minutes. So the machine is broken, there's no more pressure. In fact, the temperature dropped to below 100 degrees Celsius. Each D is now close to 30 minutes. If you use the equation to calculate, it will be a lot more precise. My graph here is not very accurate because of my freehand drawing. So it would be about 30 minutes. Times 5 cook time, 150 minutes of the process. So as you can tell how powerful it is if using high temperature short time processing. Matter of seconds to almost more than 2 hours of processing. Thank you.